Okay, here at 1320 in the video, I think this is where the data structures start to get a little bit complicated. Docstring and copy our abbey data structure in. I'll add a variable location, an int, and give it an initial value of 0. Let's examine this abbey data structure first. So it always helps me to draw things out by hand. And this data structure is a list. I'm really hoping this is going to be visible. This is Abbey. Abbey is itself a list, and it consists of 5 lists within it. And actually, I'm going to move forward a little bit in the video because I think the drawing comes up. For the location at that index, we can change the location to test different combinations of exits. Recall that in our data structure, for a single location, the values... There we go. So that's the important part. So each location is at an index inside Abbey. And for each location, it is itself a list with the name and then a description and then an exit description, which is what we want to avoid because it's redundant information with the list of exits that we then have. And this is the exit, I don't even remember, the exit to the north, the exit to the south, the exit to the east, the exit, well, I should put it in here. North exit, south exit, east exit, west exit. Let's put the indices in. So at indices 3, 4, 5, and 6, in the list for a particular location within Abbey, so for example this one, that's Abbey sub 0, that's the location we're at, sub 3. If that's a -1, there's no exit in that direction. But if it's a valid index into the Abbey data structure, so we'll just say not -1, that's going to be the index to the location we move to at that exit. Right, so that's north. So if it's -1, there's no exit to the north. And if it's not -1, there is an exit to the north. That's really all we care about for writing the exit description string. Is it -1 or is it not -1? Okay, I'm going to move on with the video. That indices 3, 4, 5, and 6 are the exits to the north, south, east, and west. A non-1 integer is a valid exit, and a -1 means there's no exit in that direction. Let's pull the exit integers out of this list into a new list consisting only of the exits. We could use a loop to build that up, but Python will allow us to slice a list. Slicing a list means extracting a subset of the list into a new list. It's like indexing, but So here, I was looking at just Abbey sub 0 sub 3, so that's the north exit integer. If I slice though, then I will get from some part of this through another part of this. So with slicing, let's just look at a simple list. If I have numbers equals, let's just say 1, 2, 3, 4, 5. Okay. When we're slicing, it's actually helpful to think of the indices in a different way. So we would normally say that's index 0, that's index 1, the 3 is at index 2, the 4 is at index 3, and the 5 is at index 4. But when you're slicing, because it's going to be start and stop, or start, stop, and step, it's up to but not including the stop. It's actually more helpful to think of this as 0 and sort of think of the indices as being between the elements of the list. So 0, 1, 2, 3, 4, and then 5 is the length of the list, right? There are 5 elements in the list. It's not a valid index, but it is a valid slice end because it's up to but not including. Okay, so let's look at some slices. If I do numbers 1, 3, that gives me a new list, which is from index 1 up to but not including index 3. And if I have my between element lines that help with slices, I can see that's starting here at 1. So that starts with this element 2. Up to but not including 3. So that would return the list 2, 3. There are default start and stop. The default start is 0, the start of the list. And the default stop is 5, the end of the list. So if I just do numbers 1, and I don't put anything there, it uses the default stop, which is the length of the list. So that would yield 2, 3, 4, 5. Okay, so in this part of the video, we're starting with Abbey sub 0, some location. So that's just going to be one of these location lists. And if I then do 3 : that uses the default stop, which is the length of the list, which in this case is 7, right? 1, 2, 3, 4, 5, 6, 7. And so that gives me from 3 through element 6 a whole new list. So Abbey sub 0 and then a slice 3 : gives me the new list of whatever these are. In this example, it's 1, 2, 3, 4. And for another location, this is going to be mostly negative ones. Okay, so that's a little mini slicing tutorial. Let's keep going. We can specify a range of values we want in our new list. I'm going to annotate a variable exits list, a list event, and then exits list equals Abbey sub location sub 3 : The first index, location, will get me to the sublist that is the data for one location. Because we've set location to 0 for now, that will be the cloister. Now the second index is the slice. I'm specifying from index 3 through the end of the list. That's 3 : If I put another value after the colon, then the slice would be the data from index 3 up to but not including the data at the value after the colon. Let me print exits list and run the program. You can see it's a list consisting of the values at indices 3 through 6 at index 0 in our data structure. Now I'm going to create a parallel list of the words that I want in the string. So direction strings is a list of strings, and that's going to equal north, south, east, west. Okay, so what I'm doing here is creating a parallel list. Parallel lists are related by index, and this actually is a really common idea in computer science. For example, if you look at data frames in R, those are vectors, which are like lists, of different kinds of data that are related by index. So these strings, north, south, east, and west, those are the strings that I'm going to want to substitute into my exit string, whatever we call that. There are exits to the north, south, east, and west. So if we're looking at parallel lists, oops, sure. Wow, I am just struggling here. Okay. Okay. There's the, what did I call it? Directions string. Let's write that. Okay. Indices. This is how they're related. I'm going to write them below. 0, 1, 2, 3. Now, I'm just going to pull out library. Okay. So library looks like this part of library that we pulled out with abbey sublocation sub 3 colon. Okay, so that for the library, just looking over at the code, 5, -1, -1, 0. Okay, so these are related by index. Now I can loop through this, which is exits list. This happens to be exits list for the library. I can loop through this, and anywhere there isn't a -1, I use the index of that element to go into the other list, the parallel list, direction string, and pull out that string. That's a string that I want in my there are exits to the directions, or exit string rather. Okay, so we can loop through this. We're going to want to loop through by index whenever we have parallel lists. So we could say for exit in exits list, but then I don't know the index of the exit. Oh, my neighbor is mowing. I do apologize for that. Okay, so I can't do it for exit in exits. I would have to do for index I in range len, and then it's the exits list. I'm missing a parentheses, colon. Okay, so now I'm going to look at the elements. So if exits list sub I is not equal to -1. So if there actually is an exit, then I'm going to append the parallel element into some other list. I don't know what I'm going to call it in the code, but let's say valid exits, for example, is a list. It's going to be a list of string, and we'll start it off at the empty list. Then I'm going to append the parallel element into valid exits. So valid exits dot append. And what am I going to append? The parallel element. So I have I'm looking at the ith element of exits list, and I'm going to append the ith element of direction string into my valid exits. So directions string sub I. So let's look at what that looks like when we step through. Okay, so for I in range, so I will start out at 0. So here's I, it starts out at 0, it's pointing to the 5 in the exits list. If exits list sub I, that's the element, is 5, is not equal to -1, 5 is not equal to -1, so valid exits, let's start that one off. This is valid exits. Starts off empty. Valid exits dot append direction string sub I. So I is still 0, so it's pointing to this guy. So we append into this list. Let's see if I can draw it this time. North. Okay, done with the loop. Go back up. I takes on the next value in the range, which is 1. So now I points to, you can think of it as pointing to both of these guys. If exits list sub I is not equal to -1, oh it is, so we're done. Go back up. I now points to the next element. If exits list sub I is not equal to -1, it is, so this code doesn't execute. Go back up. I now points here, or we can think of it as pointing to both of these. if exits list sub I is not equal to -1. Oh, it isn't. So valid exits dot append direction string sub I is 3. So now we're going to append, yay, I did it, that, and then we're done with our range. So we end up with a list of valid exits, which is exactly the elements from directions string that correlate with elements in exits list that are non-1. You can also think of this as a sort of template or filter. Like, imagine it being drawn over this, and everywhere that there's a -1 you can't see through, but all other locations you can see through. So it's a way of sort of pulling out the values from directions string that have non-1 values at the same index in exits list. Now watch, I'm probably just going to explain all that in the video now. Let's see. Why is this list parallel? Because the values in this list relate to the values in our exits list by index. The element at index 0 in exits list, 1, relates to the string north, and the value at index 1 in exits list, 2, relates to the string south, etc., for all of both lists. What I'm going to do is create a list of exits by looping over the exits list, and when there is a value that isn't -1, adding the parallel direction string's value to my list exits. So if I have 1, 2, 3, 4, then I'll end up with a list that is north, south, east, west. If I have -1, -1, -1, 1, then I'll end up with a list that's simply west. If I have -1, 0, -1, 1, then I'll end up with a list that's southwest. Let's write a loop that can iterate over both of my parallel lists. To do that, I want to create a loop control variable that will take on the indices of both lists and write the loop so it starts at the first index and ends at the last index. The indices of a list run from 0 through the length of the list -1. So I can annotate a variable I of type int. I is a common name for a variable that's going to take on a predictable sequence of values. I'll set I equal to 0. And then while I is less than len exits list colon. And then right now, let me just write print exits list sub I. And then, importantly, I need to increment I. So the next time through the loop, it will point to the next element, and eventually it will reach the length of the list and the loop will end. So I plus equals 1. This operator is a combination of addition and assignment, and it adds whatever the value is on the right to the value stored in the variable on the left and puts the result back in the variable on the left. So it's equivalent to I equals I plus 1. It's such a common operation that we have this special operator to do it, called an augmented assignment operator. Let's run that. And it prints the exits, 1 to a line. Now, what I want to do is create a list of exit strings for the exits that aren't -1. Before the loop, I'll annotate and create an empty list called exits. An empty list is simply open, close, square bracket. Inside the loop, I'm going to check if exits list sub I is not equal to -1. And if it is not equal to -1, I'll add the value from the same index in direction strings to the list. That looks like exits.append direction strings sub I. And after that loop, I'll print exits. You can see it's a list of all of the exit words. Let me change our location variable to 1. That's the church, which has 1 exit to the south. Let's run it again. And now our list consists only of the string south. Let's turn this list of exits into an exit string now. I'll annotate a variable exits string. And that exit string is going to look different depending on how many exits there are. Let's start with the simplest. If len exits equals 0, we'll set exit string to there are no exits. There's nothing like that in our Abbey right now, but a player could certainly get themselves into a situation where there are no exits in a theoretical dungeon. Now, let's do the second simplest, one exit. These are mutually exclusive conditions, so I'll use an elif. Elif len num exits equals 1, colon, and I'll set the exit string equal to there is an exit to the, and concatenate to that exit sub 0, and I'll add a period. Now, what if there are two or more? We could keep going with elif statements, or we could write a loop. A loop is better because we might want to include additional directions, such as up and down, in the future. But I'm going to write it with elif statements and leave writing it as a loop as an exercise for you. It's a little tricky as a loop because the last two directions are really a special case, so a loop mostly makes sense for a longer list of directions. Still, my loop code is only 4 lines long, and this is going to be longer and will feel very repetitive. So, elif len num exits, len exits equals 2, and I'll append into my string, there are exits to the, plus exit sub 0, plus and, plus exit sub 1, plus period. And I'll similarly build up long strings for lengths of 3 and 4. There. That's all the cases we have right now. If a line is going to be really long, it's better to break it up over multiple lines. But to do that, if you're writing an expression, you have to enclose the expression in parentheses. The line will be more readable if you put operators at the beginning of new lines and not at the end of a line. Now let's print that string and test it. For a location of 1, we get there is an exit to the south. Let's try location of 0. We get all 4 exits. I've written a testing suite that I'm going to paste in. This is an exhaustive list of all possible combinations of exits in the 4 directions. And then I have a parallel list of what the output string should be for each list in the suite. Usually we can't conduct exhaustive tests, and in that case, we would want to test edge cases, such as exits at the beginning and end of the list, no exits, all exits, exits next to each other in the list, and exits separated by other non-exits in the list, for example. I'm going to wrap a loop around my code to run all of these tests. So this loop will be another loop that's going to iterate over parallel lists. I'll use a variable called testNum to control it. I'll start it at 0, the index of the first test case, run while it's less than the length of the Abbey list, and increment it at the end of our testing, and indent all of our testing code. I've just wrapped a loop around this code that will cause the code to execute a specific number of times. At the end of it, I want to print the string that was generated and the string that we expect to have printed, which is stored at output sub testNum, the parallel element to the test case. Let's run that. And we can go through and compare each result to what we expected and see if there are any test cases for which we did not get the expected output. And then our debugging work would begin. But this looks correct. We have looked at a few loop examples, but loops are often tricky for beginning programmers to master. I'm going to link a playlist here and in the description that goes into great detail about the different kinds of loops you might write and the different situations in which you might use a loop, with lots of examples. I urge you to watch the videos in that playlist after you experiment with the concepts in this video, so you can have a well-rounded knowledge of loops. They are very powerful and you can master them with practice. I urge you to practice with loops, slicing lists, and looping over parallel lists. I recommend. Okay, so the test suite does just give us another example of parallel lists. I'm going to jump back to the test suite data structure. Okay. So you can see what I've done here is I've created sort of a dummy abbey. So it is basically, or it is the same data structure as our abbey data structure, but I've just got empty strings for the name of the abbey, the description, and the exit descriptions. So it looks like it's a list, and then it's a list with 3 empty strings for every single location. Right, so that would have been the name, the description, and the exit string. And then I've got either ones or negative ones, because all we're interested in is there a location there or is there not a location there? So the first test case is valid locations in all 4 directions. And you can see I commented off to the side that this is directions to, or exits to the north, south, east, and west. And then I just did basically all of the possible combinations of these 4. So it's sort of like the binary numbers, right? 1, 1, 1, 1, 1, 1, 1, negative 1, or 0 if you're thinking of binary numbers. 1, 1, negative 1, 1, 1, 1, negative 1, negative 1, 1, negative 1, 1, 1, 1, negative 1, 1, negative 1, 1, negative 1, negative 1, 1, so, etc. So you would just go through, because we can be exhaustive because there aren't that many, we could go through and just list out all of the possible different combinations of whether there is an exit or not an exit. So it proceeds through ... no exits, negative 1, negative 1, negative 1, negative 1, which is no exits, right? And then we have a parallel list, which I called output, of the output strings we expect for each of these test cases. So it's the same length as the abbey list, but with the expected output. So there are exits to the I didn't put a comma there, did I? I would. I'm an Oxford comma person. Okay, so that's what we expect. ... through there are no exits, or I can't see it, but I think it's there are no exits. So the element at index 0 in abbey is the test case that with the expected output of the element at index 0 in output. So they're parallel. Now I used a while loop. Maybe I haven't done for loops yet in this video series. I don't know. So we would set I equal to 0 while I is less than the length of abbey, if we want to be really careful. If we're writing defensive code and we're afraid that we made a mistake and they're not the same length, we could also do and I less than len output. And then we're going to, I can't remember. I think it's the exact same code. So we're going to pull out the list of the exit directions, sorry. So I can't remember what I called that, but directions equals abbey sub I. Okay, so the first time through that's this entire list, or well, from there to there, and then 3 colon, right, to slice off just this. So we get our directions, And then I'm just going to put a comment, run algorithm to generate directions string. And then print, or we could actually do a comparison, right? We could check if they're equal, but print output sub I, because that's the parallel element, and print generated direction string. And then, importantly, increment I. Okay, as a for loop, that's for I in range len abbey. And the for loop takes care of maintaining that I variable for us. So you don't increment, you don't initialize with a for loop. That's an advantage of a for loop. If you know in advance how many times the loop is going to execute, use a for loop because all of the control information is on that top line of the loop, and you don't need to maintain the loop control variable with an initializer and an updater. All right. Just for parallel list practice, something that I have my students do something like a list of names, and a list of ages that are parallel. We know Yoda was 900. We know Grogu is around 50, and Obi-Wan ages incredibly fast. No idea how old that man is, but let's say he's 40 years old. Okay. So then we can loop over that, I equals 0, while I less than len. We can do both, or we can just say len names. Print, and I'm going to leave this blank, and I'll put I plus equals 1 here. So how can I print Yoda is 900 years old, Grogu is 50 years old, Obi-Wan is 40 years old, or we don't know, we could put a question mark. Who knows how old Obi-Wan is? So you want to write a line that uses that index to index into both lists because they're parallel. All right. I hope that this helps you with the parallel list content in this video, which I understand is difficult to understand at first. But I think if you practice with it, it will come to make a lot of sense, and it is an important concept in computer science. Well, I'll close as I always do. As always, have fun and keep coding.